Imagine you have a tiny ball, like a grain of sand. If you fire it at a wall with two vertical slits in it, what would you expect to see on the detector screen behind it? You'd probably expect to see two lines, corresponding to the two slits the grains of sand pass through. That makes perfect sense, and it's exactly what happens. Now, let's switch from tiny balls to something much, much smaller. Let's talk about electrons, the fundamental particles that orbit the nucleus of an atom. If we fire electrons one by one at the same two slits, our classical intuition tells us we should still see two distinct lines on the screen. Each electron, like a tiny bullet, should go through either the left slit or the right slit, creating two bands on the detector. But this is where reality takes a sharp, mind-bending turn. When scientists actually performed this experiment, they didn't get two lines. Instead, they got something completely unexpected, an interference pattern. This is a series of multiple bright and dark bands, a pattern that is the hallmark of waves, not particles. Think about waves in a pond. If you drop two pebbles into the water, the ripples from each will spread out. Where the crest of one wave meets the crest of another, they'll amplify each other, creating a bigger wave. Where a crest meets a trough, they'll cancel each other out. This is interference, and it's precisely the pattern the electrons created. This result is baffling. How can individual particles, fired one at a time, create a pattern that suggests they are interfering with each other? It's as if each single electron is somehow passing through both slits simultaneously, like a wave, and then interfering with itself before hitting the screen. The electron leaves the source as a particle, seems to travel as a wave through the slits, and then lands on the detector screen as a particle again, contributing to the overall wave pattern over time. This dual nature, being both a particle and a wave, is one of the foundational principles of quantum mechanics. It suggests that at the fundamental level, reality isn't as solid and defined as we perceive it. The physicists who first encountered this were just as confused as you might be right now. They thought, this can't be right. We must be missing something. So, they decided to get clever. They wanted to know for sure which slit each electron was going through. To do this, they placed a tiny detector, a sort of microscopic camera, right by the slits. This detector's only job was to observe which path each electron took. Would it go through the left slit or the right slit? The experiment was run again, with the detector in place, firing electrons one by one. The detector worked perfectly. For each electron, it registered whether it went through the left slit or the right one. But when they looked at the final pattern on the detector's screen behind the slits, the interference pattern was gone. Completely vanished. In its place were the two simple lines they had originally expected, just like the grains of sand. The very act of measuring, of observing which slit the electron went through, forced it to behave like a particle. It was as if the electron knew it was being watched. When no one was looking, it acted like a wave, exploring all possible paths at once. But the moment an observation was made, the wave-like behavior collapsed, and it chose a single, definite path, behaving just like a simple particle. This is known as the collapse of the wave function. This raises a profoundly deep and unsettling question: does the universe behave differently when we're not looking at it? It seems to imply that reality at the quantum level is a fuzzy cloud of probabilities, a wave of potential outcomes. It only solidifies into a single, concrete state when an act of observation takes place. What does observation even mean in this context? Does it require a conscious observer, a human mind, to look at the result? This is where the topic veers into philosophical territory. Some interpretations, like the Copenhagen interpretation, suggest that observation is any interaction with a macroscopic measuring device. The interaction itself is what forces the quantum system to choose a state. However, other more provocative ideas, like the von Neumann-Wigner interpretation, have suggested that consciousness itself is the special ingredient. In this view, it is the conscious mind of the observer that collapses the wave function and brings a definite reality into being from the realm of possibilities. This idea proposes that consciousness is not just a passive observer of the universe, but an active participant in its creation. This is a stunning concept to grapple with. Could it be that the physical world is not entirely independent of our minds? Does a tree falling in a forest with no one around to hear it truly make a sound? The double-slit experiment pushes this question even further. If no conscious entity is there to observe it, is the tree even in a definite state of fallen or standing until it is observed? According to this interpretation, reality is a participatory process. The universe exists as a superposition of all possible states, and it is the act of conscious observation that selects one of these possibilities and makes it real. We are not just living in the universe, we are, in a very real sense, bringing it into focus with our attention. This isn't just a quirky thought experiment, it has been tested and retested with increasing sophistication for nearly a century. Experiments like the delayed choice quantum eraser take it even further, showing that even if we decide to look at the which path information after the particle has already hit the screen, we can retroactively erase the interference pattern. It's as if information about our future choice travels back in time to influence the particle's past behavior. The implications are staggering and stretch the limits of our everyday understanding. It challenges our fundamental assumptions about cause and effect, space and time, and the very nature of an objective, external reality. If observation creates reality, then what was the universe like before conscious observers existed? These are not easy questions, and physicists and philosophers continue to debate their meaning. There is no single, universally accepted answer. But the double-slit experiment remains the cleanest and most elegant demonstration of the strangeness of the quantum world. It serves as a stark reminder that the world on its smallest scales operates by a set of rules that are completely alien to our intuition. Reality is not the solid, predictable machine we once thought it was. It's a shimmering, probabilistic dance of potential, a world where a single particle can be in multiple places at once, and where the simple act of looking can change what you see. It forces us to confront the possibility that the boundary between the observer and the observed is not as clear as we've always believed. If you found this exploration into the fabric of reality as fascinating as I do, then be sure to subscribe to Curiosity Repo for more deep dives into the biggest questions in science and philosophy. The universe is far stranger and more wonderful than we can possibly imagine, and we are only just beginning to peek behind the curtain.